Hello, everyone. So today we are going to talk about Bootstrap. So that's the last part of the OLS slides. So the idea of Bootstrap actually quite straightforward. So Bootstrap treats the observed sample, your data, as the population, and then we sample from that population, and we can get a lot of Bootstrap sample from your data. So why do we want to do that? Well, that actually can get you a lot of useful statistics. Okay, so let's see how to do that. So suppose we have a random sample of sample size n. Then we randomly pick n integers from 1 to n and use these n integers as index to draw a Bootstrap sample. Okay, so it sounds a bit complicated, but it's actually not. So here's an example. Suppose we have a sample, we have a data, sample size is 3, so we have 3 observations. And if we sample with replacement, then we can get, for example, this is one Bootstrap sample, and perhaps we can get like W1, W2, W2. This will be another Bootstrap sample, or say W2, W2, and W3. That's another Bootstrap sample. And if you have a sample size, say even 500, you can actually get a lot of Bootstrap sample. Okay. And you can bootstrap almost anything, like estimator or any statistic. The most common application is to boot standard error, which is a very handy alternative to the delta method. Okay, so here, let's talk about Bootstrap standard error. So we already learned how to do delta method, right? If you have, say, a nonlinear combination of two estimates, the standard way to get the standard error is to use the delta method. Okay, but sometimes the nonlinear function could be very complicated, so you may want to use Bootstrap sample, which is very straightforward. Okay, so let's say we have a continuous differentiable function we call g, and we have gamma hat is g of theta hat, and theta is the estimate from the original random sample. And also let this guy, theta hat b, be the estimates from the Bootstrap sample. So in each Bootstrap sample, you can get this guy gamma hat b here, right? So it's just the whatever the nonlinear function or combination of your estimates. How to get Bootstrap's standard errors? Well, you only need to calculate the standard deviation of the gamma hat b here. Okay, so you only need to calculate the standard deviation of gamma hat b, and that actually will be the, it works like magic, but then the standard deviation actually will be the standard errors of your gamma hat. Okay. So some magic ensures that the bootstrapping procedures produce correct estimates for standard errors when your B is large enough. Right? So basically, you only need the computing power. You don't need to know any math. You don't need to do any delta method. You can get the standard errors. Okay, and in fact, the Bootstrap standard error tend to have better finite sample properties. So in other words, it may even better than your delta method standard errors. And note that you needed to adjust the resampling units if the observed sample is not entirely IID. Okay, so that is a bit advanced. If you have, say, a panel data, then you need to adjust that. For example, if you have panel data, then your resampling unit needed to be at each panel if you are willing to assume that each panels are IID. Okay. Now here is an example. So for example, if we want to do some inference on the ratio here, beta 1 head over beta 2 head. One way to get the standard error of the ratio is to use the delta method. Alternatively, you can just do bootstrapping. Okay, you can just use Bootstrap to get the standard error of the ratio. And you will see that in assignment 2. Okay. So another thing we want to talk about. Another thing about the bootstrapping is that bootstrapping provides a symptotic refinement. That means bootstrapping sometimes gives better finite sample properties for asymptotically pivotal statistics. So what is asymptotic pivotal statistic? Asymptotic pivotal statistic means the limiting distribution does not depend on unknown parameters. So for example, a standard normal distribution, is it an asymptotic pivotal statistic? Yes, right, because we know it's a normal distribution with mean 0 and standard deviation 1, so there's no unknown parameters. Similarly, like t-statistic, was statistics, they are asymptotically pivotal. Right? Test statistic, generally they are asymptotically pivotal, right? Otherwise, you won't be able to do inference. On the other hand, point estimates like your OLS estimator or the standard errors of OLS estimator, they are not asymptotically pivotal. For example, you may apply your for example, you can apply central limit theorem. You know your OLS estimator is distributed like a normal distribution, but it's centered at the beta, the true beta, with some standard errors or variance, and all these are unknown parameters, right? For here, like in this case, theta is unknown, so this estimate is not asymptotic pivotal. Okay, so what does that mean here? So that means if you put t-statistic, the bootstrap t-statistic may actually will have better finite. If you bootstrap your t-statistic, so you get your t-statistic from each bootstrap, from each of your bootstrap samples, then you can get average. Then the bootstrap t-statistic tend to have will have better finite sample properties because of these results here. On the other hand, if you bootstrap, say, like standard error, or if you want, you can even bootstrap your point estimate. there's no gain from bootstrapping, but no loss either. So your bootstrap standard errors will not be worse or better than the, say, delta method standard errors.